The title is an algebraic, essentially, you can read, but essentially as an algebraic version, or in some sense a generalization, extension of semi-regularity maps. And the reason why I choose this subject for this conference is because everything starts by a paper by Kodaira and Spencer on 59. And essentially, this paper is devoted to prove this is their main theorem. They say that this is main theorem. That means that essentially, of course, the language was the pioneer language deformation theory. Nowadays, use a somewhat different language, but essentially means that if you have an upper surface in a manifold, which is semi-regular, I will recall the definition later of semi-regularity, then essentially you can find a universal family of this with smooth basis. So in the actual language, we see that if you consider embedded deformation of a semi-regular hypersurfaces, there is no obstruction to deformation. This is a more another language. Some just few remarks that semi-regularity, so the name semi-regular comes from Italian definition by Francesco Severi, irregolare. So Severi studied the analogous problem for curves on surfaces. So I already said the semi-regular statement, equivalent statement. So wait a moment, because I cannot, otherwise I cannot see. Just 1 minute, sorry. Okay, sorry. So as I saw, that we have semi-regular hypersurface in a compact coaxial manifold as an obstructed embedded deformation. Embedded deformation, you fix the ambient, you take the ambient fix and just move inside the submanifolds. They consider only smooth case, but essentially with the same idea, we can study the same result for singular hypersurfaces. What is definition? What is the definition of semi-regular hypersurfaces? Then this is very easy. Take just the exact sequences connecting the normal bundle. N means the normal bundle of the hypersurfaces. Then take the boundary map, go from H1 of the normal bundle. This is essentially the space that contains obstruction to embedded deformations, to the second cohomology group of the structure sheaf of the ambient manifolds. Then semi-regular means that this semi-regularity map is injective. Essentially, this is a generalization of a previous result by Kodaira that says that if H1 is equal to 0, then you have no obstruction to deformation, you have unobstructed deformation. Then in some sense extend the result by assuming it is sufficient that this map has trivial kernel. As I said, actually it's not difficult to just to prove a more general result. If you have an upper surface which is not necessarily semi-regular, but if you consider the obstruction to deformation, these are essentially the subspace of the first cohomology group of the H1, then the obstruction to deformations, this is a subspace of H1, is contained in the kernel of the semi-regularity map. So semi-regularity annihilate obstructions. The corollary, this is by standard deformation theory, means that if you consider, for instance, you are in the algebraic case, a projective space, then you consider the Hilbert scheme of subvarieties of your ambient space, then the dimension is the dimension of the tangent space, which is the dimension of H0 of the normal bundle minus the dimension of the kernel. So in some sense, this is an important result which allows to study the local structure of the moduli schemes. Now, after this first result by Kodaira and Spencer, there has been later some generalization of the semi-regularity map. I mentioned only the most important two because there are other for semi-regularity for morphism and so on. But the most important are two. The first is given by Spencer Bloch in 72, that he extended the case from hypersurfaces to local I miss an important hypothesis, which should be locally complete intersection. Why? This is important just to define the map. If you have a locally complete intersection of pure codimension P, then you can define also a semi-regularity map which go from just the H1 of the normal bundle to this second cohomology group HP plus 1 of the P minus 1 of the P minus 1 holomorphic form on X. And the name semi-regularity is by the simple reason that if you consider the case P equal to 1, you recover the usual the semi-regularity map defined by Kodaira and Spencer. The second important generalization is given by Buchweitz and Flenner at the beginning of this century. The paper is published in 2003, but the preprint was at least in 99, maybe. And it is considered the case of a coherent sheaf on a complex manifold. In this case, they define a map. I will review the definition in the next slide, which is called semi-regularity map for the coherent sheaves. And again, the name of semi-regularity comes from the fact that if you take as a coherent sheaf the structure sheaf of a locally complete intersection submanifold, then this map, tau k of course go to the k here, the k is coherent, so is the case, is the same. So in this case, the tau k is trivial for k different from p minus 1, and type p minus 1 is essentially the composition. So if you can see the Bloch semi-regularity map is the composition of this component p minus 1 with this is a standard map from H1 to X2. This is sorry, this is also another mistake, should be another Y here. And essentially this essentially comes from some easy short exact sequence. But if you look at the level of deformation, you know that you have a natural transformation from embedded deformation of these surfaces to the deformation of the structure sheaf as a coherent sheaf. And this is the map at the level of obstructions. So there is a map from H0 to X1 at the level of tangent space, first order deformation. There is also a map at the level of obstructions. Is one. So essentially, this is the reason why they call also this map semi-regularity map. Just in some sense, the Bloch map is a particular case of this one. How it is defined, tau? So just consider, I defined separately the k component. So this is defined in terms of the Thea class of this coherent sheaf. This is an element of x1 of f tensor omega 1 differential class. Then you can consider the Yoneda product between x, just taking the composition about just twisted with this power of wedge sheaf. Then consider also the trace map. This is a trace of the level of f, then this go in this map. Then tau k is essentially a constant. This is essentially maybe the Buchweitz Flenner ratio is a sign, but this is not important. This is essentially it's important to take the k power of the Thea class multiplied by x and then taking the trace. Oh, sorry, it is a lot of a lot of typos. This is a trace of this product. Of course, this is an element here, and I take the trace and go here in this space. Just you go into this fact because okay, this is K. Yes, from X2 to this one. This is the definitions, and again, in both cases, either in the case of locally complete intersection and coherent sheaf, these are called semi-regular if the semi-regularity map is injective. Now, both Bloch and Buchweitz and Flenner proved that under an assumption of the ambient space of the manifold X, and specifically that Hodge-Durham sequence degenerate first page, and the subvariety or the coherent sheaf is semi-regular, then again there are no obstructions to deformation. Effectively, they prove something more, just some other stability theory, but actually this is not, in particular they prove this fact. Okay, what they not prove that different from the Kodaira Spencer case, that they not prove that semi-regularity map annihilate obstructions. This is a more stronger result. I will explain later. This was proven proved recently by Pridham and in quite an old paper, but published very recently, and in a completely different way by Ruggero Bandiera and Lepri and myself. So Pridham used derived algebraic geometry, used some more algebraic stuff. In full generality, in some particular case, for instance, as smooth submanifolds, there was also proved before. This is an important technical remark, because when I talk about obstruction, so obstruction essentially when you have a deformation factors, so infinitesimal, we consider essentially that deformation over the spectrum of local arcing rings. Then you start with some small extension, which is essentially a surjective morphism from A to B, such that the ideal, the kernel, is annihilated by the maximal ideal. Then to every small extension like this, there is an element called obstruction, which is go to the tensor product of the ideal E to the some obstruction space, for instance, in the case of locally complete intersection is H1 of the normal bundle. In the case of a coherent sheaf is X2 of FF. And for every, and we call obstruction, we consider to all small extension. For those that this map is essentially one of the fundamental exact sequence of the, remember, if the first of the second in commutative algebra. So essentially this is the differential from the ideal E to the Keller differential of this, in the case of when this map is not injective. This because there is this is the main important fact, because if this map is injective, then essentially you can, in the case where this map is injective, this essentially was proved both by Bloch and Buchweitz and Flenner, because in this case you can use some standard tool in variation of obstruction. So essentially this is the condition that allow to, in some sense, use Gauss-Manning connection just to prove some vanishing, and the vanishing of this pairing with some the RAM cohomology and so on imply that also the obstruction is annihilated. So in fact, if you consider not a generic small extension, but just a curvilinear extension, that the one essentially you consider one parameter, one deformation, this is much easier to prove such kind of result. There are several. This essentially also this argument also appear in several arguments. For instance, that one lifting theorem uses the same kind of approach. So in fact, the one within theorem give a condition from the smoothness of moduli space deformation factor, but do not give in general some condition, some result about how much big is in general the obstruction. So okay, okay. The idea is to, starting from this construction, especially from the second one by Buchweitz and Flenner, just to look at this construction from an algebraic point of view. In this case, it is useful to recall the construction that via class, via connections. So take A double star, the RAM double complex of X. X is a complex manifold, smooth. And assume for simplicity, that F has a locally free finite resolution like this. So essentially in concrete case, in almost case you have, but essentially you also have a proof without this assumption, at least in algebraic case, but of course it's much more complicated. Then so essentially it is EI are some vector bundle, in each holomorphic vector bundles, locally sheaf. Then in each one of these you choose anyone, is not important, and 1-0 connection, which is essentially a connection which is compatible with the complex structure, so that we have a component which is the bar, plus a component of type 1-0, which is another connection. Then taking the sum of this, so essentially you on every element of the resolution consider a connection. This is essentially an element of the bar of the RAM complex twisted by the RAM, so the differential form is not a complex now when you twist with the space of endomorphism of this complex. Take the component of type 1-1 of the curvature of here is the curvature of the connection, so it's delta square, just like in the classical case. Then this gives an element of the first cohomology group of this element, which is exactly the x1 of f with value for f tensor omega 1. Omega 1 because we take one form. Here the differential, essentially you should consider both the differential in the home complex, which is the commutator with delta, and usually the bar differential. Okay, then the key observation is that if you consider this data, so the algebra of differential form valued in the endomorphism of the small resolution equipped with the differential D, which is unfortunately not the same as before, but in this case D is acts like is the commutator with the connections on this is just the commuting the commutator bracket with the connection. It is operator is well defined. The bracket, the natural bracket here, and which is the curvature. This is a particular structure which is called a filter curvedly algebra. I will give a algebraic precise definition in the next slide. So in this algebraic part, we consider the following general setup. So the objects are graded vector space, graded over the integers, over a field. It can be any field. The all important fact is this characteristic should be 0 because there is a lot of exponential integrals and so on. The second fact that by filtration we always mean a decrease in filtration. from 0, 1, 2, and so on. So filtered of the natural numbers, such that the first element, the bigger element is the total space. And then we cannot assume any other condition, I not assume the completeness, and so on. Of course, every filtration, a graded vector space, induces a filtration, tensor product, homomorphism, and so on by, for instance, in a natural way, for instance, the tensor product, the filtration at the level P is just to take the tensor product of an element of the filtration for when the sum of index is at least P. So in this case, it makes sense to consider, okay, and all the morphism within filtered space, we assume that otherwise, unless otherwise say that they preserve the filtrations. Now, this fact makes sense. This perfectly makes sense the notion of filtered graded algebra. So which is an algebra object in this category. So essentially, you have a filtered vector space, and then on this we have a product which is preserve the filtration from the product you see from a map, from the tensor product, and so on. So for instance, in the case of graded filtered graded Lie algebra, so you have in this natural way. So let me give the precise definition, which is a filtered curved Lie algebra. This is a data, is a triplet of LDR, where L is a filtered graded Lie algebra, so it's a Lie algebra object in this category of filtered graded space. D from L to L is a derivation of degree plus 1, which is called predifferential. So predifferential which preserve, again, the filtrations. Predifferential because we do not assume that d square is equal to 0, but we assume that d square of an element x is the same of the commutator of some element r, where r is an element of degree lie in the first in the first subspace of the filtration, degree plus 1, it is essentially closed under this differential. This is the classical notion of curved object. In this case, the only assumption that we made in the filtered case is that the curvature should be in the first element. Otherwise, there is no. So in the curved object, you can make some good theory, only if you have some filtration. Otherwise, the structure is very poor just to work with. In particular, this assumption implies that if you take any quotient of two consecutive elements of the filtrations, taking with the predifferential d on this quotient, in this case, d square is equal to 0, and then you get a complex. And for every of this space, it makes sense to consider cohomology groups and so on. Okay, now, why is important? So, at least this is my vision of a deformation theorist. A deformation theorist is interested in this kind of data because, in some sense, it's an enhancement of the differential graded algebra, which is the first quotient, F0 quotient F1. This is, since F1 is essentially a Lie ideal, so this is a differential graded algebra, and then a differential graded algebra is related to the deformation theory nowadays, but well known, so nowadays standard fact. Okay, and so in some sense it is an enhancement, and we have an enhancement of a structure, you can deduce some important fact about the object. So let me see some examples. I give now two examples, quite easy. More tricky example will be given after the main theorem later. So of course, we have a lot of examples, but most of them are useless. So the example we're looking for are essentially the one which is should be interesting. Interesting means that if you take so this differential Graded algebra should be related to some deformation problem that you are interested to study. Otherwise, there is no interest in this study. Some examples. And useful means that this enhancement is not trivial and give and impose some restriction on this factor. Otherwise, you cannot, okay, you can prove a theorem, but you cannot, they give no concrete applications. So let me start with a very basic example, the case of holomorphic vector bundles. In this case, you take an holomorphic vector bundles, then as before, take a connection which is compatible with the holomorphic structure. And this is the bar plus a component which increase the holomorphic part by 1 on the element of this. Then take again as L the graded algebra of differential forms with value in the endomorphism or A. Consider as a predifferential just the commutator with this connection. This is again well defined. And in this case, the curvature, as in the case of curved Lie algebra, is exactly the curvature of the connections. In this case, we take the filtration, the Hodge filtration, essentially classical, so we value in the endomorphism, okay. In this case, this is an interesting example because in this case, if you take the first element of the graduated object, so the first quotient, and this is the Dolbeault resolution of the endomorphism, which is actually the differential Lie algebra that controls the formations of the vector bundles. The utility, of course, depends from how the Atiyah class of E. So, for instance, if this connection is flat, the Atiyah class is trivial, then you cannot this enhancement is completely useless. So this the utility is how much bigger, ample, or is the Atiyah class, then the more restriction give on the deformation associated with this differential Graded algebra. Okay, let me come back again to the second example is just almost immediate generalizations. You consider again a complex manifold, a locally free resolution of a coherent sheaf. Again, as before, if you take a 1-0 connection on every element of the resolution, this give, like before, taking the sum of the connection and taking just as in the case of vector bundles, you obtain in this case, and again, a filter curved Lie algebra in this case. Just taking the algebra of the RAM of differential forms with value in the home in this complex of endomorphism. This is an associative graded algebra of endomorphism. In this case, is not only Lie, but also associative case. Okay, in this case, internet is interesting because the first quotient of the filtration is the differential reality that controls the formation of F as a coherent sheaf, and again, and also in this case, depends on the Atiyah class of F, which is I mentioned before. If this class is non-trivial, then you get non-trivial condition. If it's trivial, you get nothing. Okay. Let's come back to our algebraic situations. So just looking at the example, it appears very natural to define also the Atiyah class of this data, this curved Lie algebra structure, just taking, which called AL of 8L, is an element of a second cohomology group of the second quotient of the filtration, which is the cohomology class of R. R is an element of F1, take its image in the quotient, this is a cocycle, and then they give a cohomology class, which we call this the Atiyah class. And again, just because just looking at the example, for instance, vector bundles, So, since the time is short, let me skip this fact, which is a central element. Just it is a property which in common with the usual general algebra, which is completely trivial fact. So now let's consider, given a filter curve Lie algebra, consider the symmetric algebra of L. Here L is considered just a graded vector space. Take the symmetric algebra, graded symmetric algebra generated by this. Also, these are not as the natural carries a natural filtration induced by the filtration of Hall. And for every element of Z, we consider a derivation of the algebra, which called adjoint of Z tilde. Essentially, is the only derivation that acts like the adjoint operator on L. It is extended uniquely by Leibniz, graded Leibniz rule to a derivation of the symmetric algebra. This is a explicit formula. This is the sign depends from the grading. Like this is a usual causal sign. Okay, then it makes sense to consider exactly like in the classical Lie algebra, consider the space of invariant forms, we consider for it is usual to consider the form valued in a graded vector space, not solely in the base field. There are the map from the symmetric algebra of L to the graded vector space, which each one has some degree, that preserve the filtration, and that if you apply to this on this is trivial on the element of so the composition with this derivation is trivial for every z. So essentially the natural generalization of the invariant forms on the symmetric power of a Lie algebra, like one that you study, for instance, in characteristic classes. Okay, let me give some examples. So if you have L is as before, is a graded in the Lie algebra, graded graded algebra. If you take A, which is a filter graded associative algebra, so the definition is the same, so the only difference is that the product is not Lie but associative, and take a Lie morphism from L to A, and consider a map, a trace map, trace in some sense, which is a map from A to C, such that if you take on every bracket of element of A with the image, the bracket of all element of A with the image of L is trivial. So annihilate all the bracket of this kind. Then you can consider an element, an invariant form, in this case from sim n to C, just by taking all the possible product in the associative algebra, take the symmetrization, and then apply the trace of this element. This is a very easy computation. It's proved that it's an invariant part. Just for later application, let me notice that if consider the curvature, then if you apply this invariant form to the product of n-1 power of the curvature multiplied an element x, this is the same, but taking the trace of this is a product in the symmetric algebra generated by L. This is the product in A, the second one. And it's just the same of taking the image of, is the trace of the product of the image under F. This is the product in the associative algebra. This is very easy computation. Again, now if consider now as a curved algebra with the predifferential, and C is now a complex, in this case delta square is equal to 0, then you can, like in the case of a joint derivation, you can extend D to a derivation of, which is again a predifferential, a derivation of the symmetric algebra generated by L. This is by, again, the usual causal extension. You obtain this formula, and since the square is essentially gained by adjoining this, means that if you take an invariant forms, this vanishes on t square of anything, and then if you take all the homomorphism from the symmetric the invariant forms, if it is a subspace, then this is essentially a subcomplex. In this case, you have the usual formula from the induced differential is a real differential. So d square is equal to 0. So it makes sense here to consider a closed and exact element. Now, let me, I can now state the main theorem of this talk. Is this, that again, you have a filtered curved Lie algebra, then and consider a closed, which is essentially as before. So closed means that the commute with the differential and L invariant map of degree 0 from some symmetric power k plus 1 in this case to this complex of vector spaces. Then you can take this product, the k power of the curvature and x multiplied by x. This is essentially is not relevant. This scalar multiplication. Define this map. This go through this is well defined from the first quotient of the filtration to this quotient of the filtration in the target. Of course, shifted by degree 2k. Otherwise, this is not, because I want sigma cap of degree 0. Now the theorem means that this is which is essentially a morphism of differential graded vector space. If it is can be lifted to an infinity morphism, where the target, not C, but also this target, is considered as an abelian de Gilles algebra, so we have no bracket here. Here in the domain you have a bracket, non-trivial bracket. In the target you have no bracket. Essentially, so you know when you have if you have a map, for instance, from differential Gradient algebra, which is not limorphism, but is also a morphic complex vector space, it is interesting to know if this, so in some sense, is a weak morphism of weak algebra, so a morphism in the homotopy category. In fact, for people which is not, I remind this for people which is not practical of this fact. L-infinity morphism can be think like a morphism in the homotopy category of differential Gradient algebra. Homotopy category is where is the category localized by quasi-isomorphisms and so on, because we have a lot of invariant theorem. Okay, the second remark is that the main theorem for k is equal to 0, the main theorem is there is nothing to prove, because the map sigma 0 is just a morphism of differential Gradient algebra. So there is nothing to prove. There's another remark from the second case, but I can skip because the time is not much. Okay. The fourth remark is quite important, because if you look, so the image of sigma k, so the linear part, is contained in this subcomplex, which is an element of the quotient of two competitive elements of the filtration. But if you consider all the higher component, so the higher Taylor coefficient del infinity morphism, this is not true. In general, it's not true. They are contained also in the ball space. This is essentially, so of course, remind to the Griffith's transversality theorem. So you may have a variation of the structure, the differential, the first part is just like in the first part, but all the map, period map, no, lie in a bigger space. Another important fact is that this algebraic structure may appear quite exotic, but if you look at example, it is very common to find this curved structure in many geometric interesting case. The difficult to find in the example is to find non-trivial invariant map. This is the usual, apparently, at least in the example which I was investigated, is the more difficult part. So for fine example. So in some cases you can find, if you start from a deformation problem and consider differential algebra, take this enhancement, which is usually easy to produce, then the only invariant map that you can construct are the one which are from some simple deformation problem. So essentially, it's a composition with some forgetful morphism. For instance, if you consider flags or flags of vector bundles, then of course it's an interesting problem. The only invariant form that you usually are able to do are the ones which are essentially the trace of the description from every element of the filtration. So in this case, there is no particular, not more important case. Anyway, like in the case of Buchweitz and Flenner, we can define the semi-regularity map associated to this data. Let me now consider two different semi-regularity maps, which I call strong and weak. So the formula for both of them is the same. The only difference is in the target. So the formula is just, for instance, take the k power of the curvature, which is of the k power of the Artia class, which is essentially, since I take the quotient by the fk plus 1 of the pressure is just the same. Apply the invariant form, and they take the element of this cohomology. This is easy to see, which are cocycle and so on. Clearly, the weak is the composition of the strong by the natural inclusion of this cohomology group given by the filtration and so on. So because I make this distinction, because we have, if you are interested in geometric application, just we are passing to deformation theory, you have that the theorem implies that the weak semi-regularity map, which go from the second cohomology group of the basic differential algebra to this product of cohomology group, annihilate so all the obstruction belong in the kernel of the weak semi-regularity map. Of course, if the spectral sequence of the complex C degenerate at the first page, then the map from the target of the strong go injectively onto the target of the weak, and then also the same conclusion apply also to the strong semi-regularity map. But this is essentially a geometric condition. So essentially, like in the case of just geometric case for a vector bundle of some manifolds, if you have essentially, if you want to prove the vanishing of obstruction, we have first a purely deformation theoretic statement, which concerns the weak, and then a geometric effect, which control, for instance, the Keller or projective and so on. So this is a very now standard, very nowadays considered very standard result. Okay, let me give two applications to geometric element. So the first is essentially the case which I mentioned before. Take a coherent sheaf on a smooth projective manner. I take projective just for simplicity, just otherwise you have make some other more technical complicated assumptions. Then the semi-regularity map, or defined by Buchweitz and Flenner, annihilate all the obstruction for every case. So they are essentially some numbers, so we have some, at least some, how much, so the dimension of x minus 2, so essentially, because minus 1, minus 2, I don't know, so the number of semi-regularity map, all of this map annihilate obstruction. So the fact is, this case, the proof is just an application of the corollary, because as before, take a locally free resolution, take this map, the differential form in the endomorphism form, take as a target complex is just the RAM complex of your manifold, and equipped by the usual Hodge filtration. Take as invariant form this, since this is also a this is also a associative algebra. Take the trace of the symmetrization of this element, of this product. Then in this case, just by standard compute, in this case, you obtain that the Attia class of this algebra is the same as the Attia class of the coherent sheaf. The second cohomology group of this algebra is X2, and the group H2 plus 2k of the k element of the filter, the k of the k quotient of the filtration C is exactly the group AK plus 1 omega k. So you just look at it, you obtain the map from defined by Buchweitz and Flenner. Let me give a second application, a second example. See, I can give this example. Maybe I can go. So I have 15, 20 minutes. I mean, okay, let me go. It is another quite nice example, according in my opinion. So consider a twisted bundle. So twisted means that you fix a generic locally free sheaf instead of omega 1. And twisted bundles over this pair is a pair given by a vector bundle E and a section of the endomorphism of E tensor L, such that if you take the wedge of theta with itself is equal to 0 in this space. The endomorphism tends by 2. If you take for omega 1, you recover the classical deformation of X bundle on higher dimensional manifold. In case of curve, for cars, this condition is completely automatically satisfied, so there is nothing to consider. Now, also in this case, we can construct a filter covering algebra in this way. First, we take the acyclic complex with the bundle, the sheaf L in degree 1 and degree 2, and delta is the tautological isomorphism. This is a complex, acyclic. Take the symmetric algebra, and this is you can write this is a graded algebra. It is decomposed by as a sum of homogeneous component. Bij is essentially the part, so this is a node, this is odd degree, so when you consider the symmetric part, we obtain the wedge product. This is even degree, you obtain the symmetric product. And then Bij is isomorphic to this tensor product, and the element of Bij are degree I plus 2j, because this L is of degree 2. Now consider again the filtration where the symmetric Fp, the symmetric part is at least P. This is given the filtration. As again, consider now as a filter covering algebra the Dolbeau resolution of this complex. Also, this is an infinite dimensional, but okay, you can take by degree and then take the direct sum. So in some sense, obvious sense. So this is written by should be intended cum grano salis. So the filtration, just consider the filtration of the sheaf B. Here we consider the pre-differential, the differential given by the Dolbeau. This delta is so in this case delta is not is the differential of this in the symmetric algebra B. Delta is the differential on B, and then the commutator with the X field theta, the sections. Theta here it is considered as an element of this global section of this vector. Since the condition that which is theta is holomorphic, theta which is equal to 0 because it's a hot degree, so this essentially is 2 times theta wedge eta. And then within this fact, the curvature is exactly the differential by delta of theta. So this essentially is the same of theta. Since delta is tautological, is essentially theta, but now it's not considered as an element of this. So in B01 and not in B10. So because I consider as an element of this. So it's the same object, but considered in a different homogeneous component. This is the curvature of the fields. Now it is interesting because if I take the first quotient this is a differential Gaussian algebra that so I put away all the symmetric part, so it remains only the wedge, the external power of L. This is a differential Gaussian algebra, and this exactly controls the deformation of this pair as a twisted band. So this is a differential Gaussian algebra that controls the deformations of the X bundles. In this case, okay. Now let's consider a trace. So the usual trace is just the trace of an endomorphism extended by linearity. And as above, considers invariant form the trace of the symmetrization. And then we are exactly in the position of apply the corollary, the main theorem. And this implies that the weak semi-regularity map from the second cohomology group to the group 2 plus k of this of the Dolbeau resolution of this sheaves, graded sheaf, annihilate all the obstruction. This description is quite obscure, but we can make very concrete. And in fact, you should be some computation, but not essentially very easy. So if you take an element of H2, is essentially is represented by a sum of 3 elements. Each one of these xi is a differential form of type 0y, and of course by degree reason also extend here in this case. Now take the k power of the curvature theta. This is an element of the endomorphic, is a section of the endomorphic, essentially is allomorphic section, but anyway, the endomorphic tends to the symmetric k power of L. Then, if I take the group, the target group, it splits as a direct sum of two groups. The first is H1 of symmetric power of L, and plus the global section, the homomorphic section of the image of this product. So essentially, this essentially is delta. But anyway, it's better to write as a product. I don't know if it is so. Probably people which experience representation theory should be. It is very common since this image essentially is a Schur functor. One of I don't remember if there is essentially one. We are all the square on the tableau Young are in vertical plus one. So the first two. So that it is Schur functor of the sorry. Okay, 2 1 1 1 1. Okay, so this decomposition, this partition of n plus 2. Okay, in this case, the component of the semi-regularity map are two components. The first is take exactly the trace of the k power of the R tensor, take the symmetric product with x1 is the element which is 0, 1 form, and the second component, the one of h0 of G, is again the trace, the k power of the Higgs field star this applying this product, this map x0 to the component x0. The component x2 is not considered here because it is x2 is essentially related with the formation of the bundle without any reference to the Higgs field. So it is essentially just to have a semi-regularity map which involve x2, which should make a more complicated construction, taking all not only the Dolbeau resolution, but all the RAM format, and consider also a connection and on the curvature and and so on, like before. Okay, I have maybe 10 minutes. Let me give a very so I can, of course, the proof is algebraic. It's the proof. It's there are some computation. So essentially the main difficulty is just difficulty in the proof is just to check, to guess what are the correct take to define. But once you have the definition, just to verify, or some object, just to verify that works, that everything goes. It's quite elementary. So we have three steps. So the first is just to prove a similar result for curved pairs. I'll give you the definition later. The second is prove that if you take the universal enveloping algebra of L, this is a curved pairs, and then apply a filtered version of the Poincaré-Birkhoff isomorphism. So what is a curved pairs? Is essentially a filtered curve associative algebra with inside a Lie subalgebra. So this the structure should be compatible in some sense that the curvature L should belongs to the subalgebra L. So you take a filter curve associative algebra with plus a grade Lie subalgebra such that the curvature belongs to L. This is an element of the Lie algebra. Again, you have the composition, the R should be closed by the predifferential, and the square should be the bracket with the curvature, and so on. Now, in this case, if you take again a complex vector space, here do not consider invariant map, but consider a trace map, which is a morphism, which preserves filtration as usual, such that all the commutator of element of L of the element of A go to 0. So annihilate the bracket of this element, and this should commute with the differential as in case above. Then there is the second main theorem. So this the same theorem but applied to this curved pairs means that if you have a curved pairs and a trace map, then again you can define this map, this amorphism of complexes, just by taking, in this case, we have just taken the trace of the multiplication k power times x, and this is the linear component of an L infinity morphism. Okay. This is again proof is technical. If maybe I had no time to give an idea at the end, but this is just the first step. The second step means just to use the universal enveloping algebra, define the universal enveloping algebra as in the classical way. Just take the tensor algebra, quotient the ideal generated by element of this element. Again, here we have a filtration, natural filtration, induced by the filtration of L. Again, the predifferential D extend to again by Leibniz rule, to a predifferential of the universal enveloping algebra, and this, in this case, you have that L, so by, L is so the map from Edwin and Bloch, you may consider L as just a subalgebra of L by the Poincaré-Birkhoff. In this case, taking this and this, just the unit element is again a filter curved pairs. The Poincaré-Birkhoff means that if you take, so this is you have a natural map from L to UL, then this is so essentially the formulation given by Quillen of the Poincaré-Birkhoff, which holds only in characteristic 0. Take this map just by taking the symmetrization of all over all the permutation on this map, and then this is an isomorphism of filtered graded vector space. As you know, it is not a morphism of algebra, it's a morphism of coalgebra, but this is not relevant for application. Moreover, this is just a simple remark. If you look at what the composition of this adjoint map with an element x is the same of taking the bracket in the universal enveloping algebra. The image is obtained taking the algebra. And this is commuted with the predifferential. The proof is straightforward. This is not case. From this theorem means that if I take a morphism from this symmetric algebra, this is a closed invariant if and only if the composition with the PBW isomorphism from the universal envelope algebra is a trace map for this curved pair. And this allows to reduce the first theorem to the second. How much time I have? Sorry. Do you hear me?
Probably -1 minute.
-1, perfect. Okay. So anyway, so the idea is of the proof from associative case is essentially that I interrupt the condivision. Is essentially it's very similar to the theory characteristic classes. So if you have in this case you can take if you take the space of all pre-L infinity morphism from L to A, so L is a algebra, A is the ambient space of these curved pairs. Take not only those of degree 0, but take all the pre-L infinity is a morphism from the co-commutative coadjuvant generated to A. Take also not all of the morphisms of every degree. This all the space as a structure of a curved associative algebra, and then you take some Chern-Simons form associated to a splitting from from the quotient L to F1 to L, and this give after some computation gives 1. So essentially the other difficulty is just to guess what is the right definition. Then you have some quite boring but elementary proof. Thank you.
Thank you, Marco.